Hello everyone, this is Aditya. So, today is week 11 of our live lecture interaction sessions. And today I'm going to be discussing the 11th assignment which was forwarded to you previous year. Feel free to pose in your doubts and I'll try to uh, address them. So, in the first question, it's given to you that you have a transformer with you, and the transformer can be represented in this particular form. Right, so you have your V1 here and you have your X1 R1 XM RM, right, and you have your V2 over here. Now what happens in a transformer is that this when it's an open configuration, that there is no circuit, no load connected at the secondary, right? In that particular case, what happens is that the only current which is flowing is the current flowing in this particular winding, because this winding, let me call it I, because this winding, let me call it I1 is equals to 0 because I2 is equals to 0, right, because it's an open loop condition. So no current can flow into the primary winding because the secondary is an open condition. So the only current which is flowing in the circuit is to provide for the magnetization current, right, the XM, and then the core losses, right. So if you see the value of X1 and R1 are negligible compared to the value of XM and RM, right? So this particular circuit of transformer can be remodified, can be modified into something like this, right? So it can be remodified into something like this without uh, causing any errors to, like, any meaningful errors to creep into the result. And this modification kind of simplifies our calculations, right? So this is done during the no load kind of testing, right? So this question is related to no load condition, so you can very well write you can very well draw the transformer equivalent circuit to be in this particular format, right? Now, if you have this particular configuration and it's given to you that voltage, that is the voltage V1 by I, V1 by I is given to you, right? Or it's not given to you, but then you can always find the value of V1 by I. What would it be? It would be 400 uh, at an angle of 0, right, and 2 at an angle of minus 85. So please remember that it's a peak value which is given to you, but then you can always convert it to RMS. So you can write it as 400 divided by root 2 and then 2 at an angle of minus 85 divided by root 2. Anyways, the root 2 and root 2 are going to cancel out and you will be left with V by I is equal to, let me just do it, 400 divided by 2 at an angle of minus 85. Yeah, so it's equal to 17.43 plus 199.238 I or J, whatever you feel like calling it, right? So you see over here that V by I is nothing but the effective value of R effective plus J X effective. But we know that the value of R effective and J this is going to be practically this thing, right? So from because this will not be conducting, right? Because the current, as we had discussed previously, is zero in this particular path. So this no current is going to flow in here. So the only path where the current is flowing is this path, right? And the XM and RM will be equal to R effective, RM and XM, right? So from here you can understand that the value of this is nothing but equivalent, right? So from here you can very well understand that the value of xm is equal to approximately equal to 199.238 J, right? So this is your answer of magnetization inductance in omega, right? Which is not provided in any of the options mentioned in the question. So therefore the correct answer is D, that is none of the above. I'm hoping that this is clear to everyone. If not, feel free to pose in your queries in the next meeting, and then I'll try to address them. So in question number 2, it's given to you that you have a two-winding transformer. However, it is reconnected in such a fashion that it becomes an auto transformer, right? So we know that in an auto transformer there is no magnetic isolation, right? So the two windings are connected, so the power is transferred in an auto transformer. So you have let me just write it what I'm saying. So you have a transformer, right? The power is transferred, power transfer is by magnetic effect, but in an auto transformer the power transfer is by magnetic plus electric. So for example, if you have like let's say let's take the take the question as an example in our case, right? So you have your 3300 volt on the primary and 230 volt on the secondary, right? And it's given in the question that it's connected in such a fashion that the overall voltage becomes 3.53. Now how can it happen? It can happen only when these two are connected such that the polarities add up, right? So we have seen in dot convention, right, that if the dots are in the correct fashion, then the voltage can add up, right? So here you had a dot, and here if you have a dot, then overall the potential will add up. So this was 3300, correct? And this thing was 230. So overall, and this is your effective output V2. Now it will become your V2. So V2 will be equal to 3300 plus 230. That is equal to 3530 volt, right? Now we know that the current is not going to change, right? So the current is in this particular section will be I1 and this will be I2. This will be I2. But what is I1? I1 is nothing but 50. Okay, something is there. So what is I1? I1 is nothing but 50 divided by 50 kVA, right? So 50,000 divided by this thing, right? So it will be equal to let me just do the calculation. So 50,000 divided by 3300, 15.15, right? And I2 will be equal to 50,000 divided by 230, correct? So 50,000 divided by 230 is equal to 217.39 ampere, right? Now what is the kVA output at the secondary? So secondary, we know that the voltage, new voltage is this and the current is equals to this. Therefore the kVA is going to be 3.53 kilovolt into 217.39, correct? Now 3.53 and you multiply it, you will get 767.39 kVA. Alright, so this is how you deal with auto transformers, that you take you configure this auto transformer in such a manner that it meets your requirement. So if the requirement at the output is 3.53, the windings are going to be connected in this particular fashion. However, if the requirement is, let's say, something else, if the requirement was that the output voltage must be equal to 3300 minus 230, uh, 3300 minus 230, that is equals to 3070, then in that case you would have connected your auto transformer something like this, right? In that case you would have got at the output 3070 volt, correct? So based on what your requirement is, you are connecting the windings of the transformer to ensure that the dot polarities meet your requirement, and then you can do your calculations. So here in this particular case the power is transferred by magnetization. So this and this are still magnetically coupled, right? So the power is still magnetically flowing, but then there is an excess power which is just the multiplication of this current into this entire voltage. This current into this entire voltage. So I'm hoping that this is also clear to you guys. If there is any query, feel free to ask in the next class. So in question number 3, you have to figure out what is the voltage regulation, right? Now what is voltage regulation? So voltage regulation is, let's say you have your transformer, right? Now this transformer will have some R, it will have some X, and then it will have some load connected at this point, right? With the voltage of V2, right? So if the load is equal to 0, if load is equal to 0, then the V2 is equals to E2, right? That this is the no load voltage. And if there is some load at the output, load not equal to 0, then V2 is equals to V2. There is some voltage, right? V2. So V2 at loaded condition. Now voltage regulation is nothing but E2 minus V2 under loaded condition divided by E2. This is your voltage regulation, right? Now how do you determine this particular quantity? So for determination of this, you can use something which is known as phasor, right? So you have your V2 over here. Let's say you have your current which is flowing at a lagging power factor, right? So I2 is flowing something like this at a lagging power factor. Then if there is some resistance in the circuit, then there will be an I2R drop, and if there is some reactance in this if there is some like reactance in the circuit, then it will be at an angle of 90 degree away from this, and you will have something like this E2, right? So this is your E2 and this is your like phasor which is coming out from V2 and then meeting the E2 over there. So how do you figure out the difference between these two quantities? Like how do you figure that out? So if you'll see, then I can write this thing as nothing but theta, right? And I can get this particular quantity, right, as, so this is let me call it IR I2R cos theta is your vertical part here, right, A, and the B will be equal to I2 x2 sine theta, right, is equals to B, and the if you'll see this particular point, you are reaching this particular point. This particular point is same thing as this particular point because it's going in a big circle, right? So with the center at this particular point. So you can write that the difference in E2 minus V2 is equal to, or rather you can write E2 is equal to V2 plus A plus B, right? Because we have discussed that both of these are radius. So this is one radius and V2 plus A plus B is another radius, right? So you can write E2 is equals to V2 plus A plus B, right? Now from here I can deduce this particular equation, right? So this equation will in that case be nothing but um I2R cos theta plus I2x sine theta divided by E2. Now also from here you can write that this is nothing but ER cos theta plus EX sine theta. What is ER and EX? This is nothing but per unit quantity, right? So we see that ER is equals to I into R divided by E2, correct? But we know that E2 divided by I2 is R base, right? So therefore you can write that resistance divided by R base is nothing but the per unit value of resistance which is given by ER, right? So similarly you can figure out EX, that is the per unit value of reactance, right? So this is your voltage regulation. So try to remember this formula, and this voltage regulation formula is valid when you have your lagging power factor. If there is a leading power factor, it will just change to a negative sign. So it will be ER cos theta minus EX sin theta. That is all. So depending upon whether it is lagging or leading, the formula is going to change, right? Now with the advantage of this, like if you have this particular formula with you, you can try to figure out the solution of this question. So let's try to address that. Okay, let me introduce a new slide over here. Just 1 minute. All right. So as we had seen before, the formula is voltage regulation is equals to ER cos theta plus EX sin theta, right? Now what is ER and EX, right? So it's given to you that the leakage resistance referred to the low voltage side is 0.04, and uh, 0.8 is the lagging power factor of the load, right? So the power factor is given to you, that is cos theta is given to you as 0.8. Therefore, sin theta is equals to 0.6. These two information is given to you. The only thing which you require to find is ER and EX, right? So what is Z base? Z base is equals to MVA divided by kV square, right? So what is MVA? MVA is equals to 0.5. What is voltage in kilovolts? It is 0.5 whole square. So, oh, okay, I wrote it in the just let me erase it. So Z base is nothing but kV square divided by MVA, and it's equals to 0.5 whole square divided by 0.5 is equals to 0.5, right? And you have your Z base over here, right? So what is R? R base is nothing but value of R ER, or rather let me, so I have named it as ER, so let me call it ER. ER is nothing but R base, Z base or rather. So this will be equal to 0.04 divided by 0.5, which is nothing but 0.08. Now if you have your ER as this, then I also know that ER square plus EX square is equals to Z square, right? Therefore the Z value is given in the question as 0.1, right? So this is given to you as 0.1, and you have figured out that ER is equals to this quantity. Therefore EX you can figure it out from here as 0.6. Now you have your ER with you, ER with you. This is your ER, and you have your EX with you. You have your cos theta with you. You have your sin theta with you. You can just put it into this particular equation and then try to solve it. You will end up getting the value of voltage regulation as 0.1, or in percentage it is equals to 10%. So that gives your C as your correct answer, and then that's there. So I'm hoping that this is clear to everyone. If not, feel free to pose questions on it in the next time we are meeting. So question number 4 is stating that you have your transformer, single phase transformer, and it is undergoing an open circuit test and a short circuit test. So you have to figure out the magnetization reactance referred to the low voltage side. All right. So whenever you are doing what do you call it, the open circuit test, it has to be on the low voltage side, right? Now why it is so? Because you need to impress with a smaller voltage. So the open circuit test is always conducted on the low voltage side. So here you can see that the open circuit test has been conducted on the low voltage side. And similarly, like the short circuit test is always conducted on the high voltage side. The reason is that the current demand from the source is going to be minimum. So that is why it's connected on the high voltage side, right? So so let's proceed here. So the open circuit voltage V square divided by the resistance R is going to give me the core loss, right? P core loss. And why is that the case? Because we have already seen that in open circuit test the effective transformer can be minimized to this particular equivalent circuit. So you have your voltage V open circuit voltage. So VOC over here, VOC whole square divided by R core is equals to power of the core loss power, right? And this is given to you as 50 watt, right? Now if this is the situation, then I can figure out the resistance, right? So the resistance from here R core is nothing but equal to 1250. So you just try to solve this particular thing, you'll get this value, right? Now if you have the core resistance like this, and then you also know that I input, so I input is given to you as 0.8 ampere, correct? So VOC divided by I input is equals to 0.8 is equals to I M square plus I R square, right? And you can take under root of it. So but the value of IR we can figure out, right? So the value of IR is nothing but 250 divided by 1250. This is your IR, so you can square it, and you have your IM square. You have taken your under root, and you can equate it to the input current, right? So this is your IM, this is your IR, correct? And you can equate it to 0.8, and once you solve this particular quadratic equation, you will get to the value of IM. So let me just try to solve it. So 0.8 square divided minus 250 divided by 1250 whole square, right? And under root of this is equal to IM is equal to 0.7745. Now this IM is nothing but V divided by XM, right? But the value of V is given to you. V is known to you, right? V is 250. So 250 divided by 0.7745 is equal to XM. So 250 divided by answer is equals to 322.74. So this particular thing falls in this particular bracket, right? So that becomes your answer. So for question number 4, the answer is equals to C. So what's the thing which you need to remember while solving these kinds of questions? That when you are doing the open circuit test, it has to be conducted on the low voltage side. When you are conducting the short circuit test, it has to be conducted on the high voltage side, right? This is the only thing which you have to remember in this particular in these particular type of questions. Other things like are straightforward. It follows from basic understanding of KCL and KVL, right? So let's go forward. So the same question is there in this question number 5. The same question is repeated, but the demand is little different. So it's asking you to figure out the kVA loading at which the transformer will give you your maximum efficiency. Now this is something which you need to kind of refer to your professor notes, right? So if you'll refer to the notes given by your professor, you will figure out that efficiency is maximum is max when copper loss is equal to core loss. So if this is the situation, then your efficiency is going to be maximum, right? So how to determine the loading at which it's giving the maximum efficiency? So if you have your like I can say that my regular copper loss, that is my rated copper loss, right? So P rated, if this is my P rated copper loss, right, and it's running at loading of X%, right, then the copper loss will be equal to P copper loss is equal to at loading X% is equal to X square into P rated, correct? So so from equation number 1 I will write that when the transformer is running at X% loading, then if X square into P rated is equal to P core, if this is the situation, right, if this is the situation, because this is your new copper loss, right, if this is the situation, then I can say that you have to have an X% loading to ensure that the efficiency is maximum for N max. So basically you have to figure out the percentage loading X here such that the copper loss at that particular loading, that is at X% loading, is equal to the copper loss. So I'm hoping that you understood it. Now the question arises how to figure this out. What is the value of this X? How to figure this out, right? So your rated current is going to be equal to 10 kVA divided by 2500 volt, right? On the low voltage side. Sorry, on the high voltage side. So 10 kVA divided by 2500 is equal to 4 ampere, right? Now what is the short circuit current? Short circuit current is 3 ampere, right? So the short circuit current is lower than the rated value of current, right? So what is the rated copper loss? So the rated copper loss is going to be P rated copper loss is going to be 4 divided by 3 whole square into 45 watt. Now why is this the case? Why is it whole square? Because I know that the copper losses are I square R, right? So if the current was actually 4 ampere instead of 3 ampere, then the copper loss would be 4 by 3 times the whole square of 45, right? So that's what I've written, and this will be equal to some value. Let me just figure it out. So 4 divided by 3 whole square, 4 divided by 3 whole 4 divided by 3 whole square into 45 is equal to 80 watt, right? Now I have written that for X% loading, X square into P rated is equals to P core loss, right? And the core loss is given to you. The core loss has been evaluated at 250, which is the same voltage as the rated voltage of the transformer. So no need to do any further calculations there. You can just write the P core loss is equals to 50 watt, and the X can be evaluated as 50 divided by 80 under root, right? So you can write that X is equals to 50 divided by 80, that is equal to X is equals to 0.79. All right. So in terms of percentage, it will be equal to like 79%, or you can write it as uh, KVA, since it has been asked to figure out the KVA rating. So this is slightly mistaken over here. This would be coming as 79, right? So this is wrong over here. This would come out to be 7.9 kVA, right? Because x into 10 kVA is 7.9, not 8.3. So this is kind of wrong. So I'm hoping that this was also clear to you guys. If there is any question, feel free to ask. Okay. Why is it not moving forward? Yeah. Hmm. So in this particular question, it's given to you that a 10 kVA single phase transformer, same the transformer remains the same. Find the percentage efficiency at 85% of the full load at 0.8 power factor leading, right? So I know that efficiency is equals to P out divided by P out plus losses, and you can multiply it with 100% if you want to get it in percentage, right? But essentially it is power output divided by power output, and what's the losses. So what is power output? Power output is equals to power output is equals to Vi cos theta, right? And since it is running at 0.85 times of the full load, therefore power output will be equal to 0.85. In our case, power output at loading is equals to 0.85 Vi cos theta. So this is what will be the power output, and you can put in the values. So 0.85 into Vi is given to you as 10 power 4, right? So Vi into cos theta is also given to you 0.85 leading. So this is your power output at loading. And losses, what is the losses? So the losses is core loss plus copper loss. So core loss is given to you as fixed, right? Because like you're not changing the voltage. So the voltage is remaining the same, therefore the core loss is going to remain the same as 50. So no changes there. However, the copper loss will change. The copper loss is like we have determined it in the previous question. So the copper loss was at full load. At full load, the copper loss was 80 watt, right? So at 85% of the full load, it will be nothing but 0.85 whole square into 80. So you put these two quantities in this equation. Let me call this equation number 1. You put the loading and then the losses P output. This is the P output and the losses in equation number 1, and then try to solve it. You will get the efficiency value as 98.52%, right? Now this particular thing falls in the bracket of this, and therefore A becomes your correct answer. So I'm hoping that this was also clear to you guys. If there is any query, feel free to ask, and I'll try to solve them. Take the you can now move to the session which is now provided by my colleague, and try to understand the questions from question number 7 to question number 12. Thank you guys.